Hello and welcome to your third video lecture for Chem 371 in 2019. So this lecture is going to be about the t-statistic and how we calculate confidence intervals for the case where we don't have a good estimate of sigma. So I'm going to start by just giving you a few reminders. So I'll remind you that mu we've been using to talk about the population mean, and x is what we use to talk about the sample mean. So mu is infinite measurements, x is something less than infinite measurements. In practice, x approaches mu when you have 20 or 25 measurements. Similarly, sigma is the population standard deviation, and s is the sample standard deviation. And we've also been denoting x equals some single measurement. So what we've been talking about in class is how our confidence in our number changes as a function of number of observations. And in class, we've seen that as n goes towards infinity, x approaches mu in a known way, where we have the standard deviation of the mean is the population standard deviation divided by the square root of n. So we've been using this statistic called z to talk about how far we are from the mean. And we define that as x minus mu over sigma. So that is the distance of any one observation from the population mean as a fraction of sigma. Then, if we know sigma, we can calculate the confidence interval. And that is confidence interval for mu equals the average you observe plus or minus sigma times z divided by the square root of the number of measurements. So now we have to consider the special case. What if we don't know sigma? So just as the average that you observe approaches the population mean when n goes to infinity, so does s approaches the true population standard deviation as n approaches infinity. And it does so in much the same functional form that x approaches mu. So to think about this, we define a new variable called t. And it looks a whole lot like z, except that instead of using sigma, we're using s, which is the standard deviation that we've determined for our sample. So written this way, this t doesn't make much sense because you would have to have made more than one measurement to obtain any values for s. But if you've done 5 measurements, for example, then you could calculate t for any one measurement. That's not super useful. A slightly more useful form that will come back in a future video is called the t-statistic. And that is the average you measure minus the population mean over s divided by the number of measurements you made. This is called the t-statistic. It is very useful in certain statistical tests. Those are the subject of a future video. For now, what we're going to do is think about how we report confidence intervals for the case where we don't know sigma. So confidence intervals using t then look very similar to what we did using z, except that instead of sigma, we're going to use s, and instead of z, we're going to use this t statistic. So we can write mu, the confidence interval for mu, equals the average value we observed plus or minus t s over square root of n. And so the functional form of this looks very similar. The t value comes from a t table instead of a z table. And t, the factor by which you have to multiply your standard deviation to find the range that you're confident of, is larger than z. T is larger than z, and for small n, t is much, much larger than z. For larger n, t approaches z. So now we're going to take a moment and look at the t table in your book. This is on page 898. And I'll just note that here, so this table depends on the degrees of freedom. So the degrees of freedom are defined just as they are when you're calculating the standard deviation of a finite set of observations. So if you've made 2 measurements, then you will be calculating the standard deviation of 2 numbers. You have a single degree of freedom. And so if you're talking about your 80% confidence interval, you will multiply the standard deviation that you've observed by 3.08 to get that confidence interval. And then I'll note that by the time we get down here to, basically anything 10 and higher, we're within like 10% of the eventual z value. And as we get infinite measurements, this equation collapses to the same equation that we used for z. So you need to know not only the confidence interval you want, but also the degrees of freedom you have. And that's just because as you make more measurements, S becomes a better estimate of sigma, and so we don't have to add the additional uncertainty. We have to add additional uncertainty using t when we have tried to estimate S using an insufficient number of measurements. So if this is all really confusing, I would recommend that you take a stab at this example problem. The solution is here, and I think once you've done it once, it will make a lot more sense, but it is identical to calculating confidence intervals using z. It's just that you have to use a slightly different table, and you have to think about how many measurements you made, as opposed to z, where you assume that you know what sigma is.